This is Applied Calculus, Lesson 1-4, Polynomial and Rational Functions. We start with the definition of a polynomial function, which is a function that can be written in this form that you see here. F of x equals a sub n of x to the nth power plus a sub n minus 1 plus times x to the n minus 1 power, and so on, until you get a1 x to the first power. A sub 0 is understood to have an x to the 0 power next to it, because anything to the 0 power is 1, and that would leave just the coefficient behind, the a sub 0. Now, the thing about polynomials is that all of the exponents must be positive whole numbers. That means that n must be large enough so that n minus 1 and n minus 2 are positive whole numbers. And the only exception is the constant term has x to the 0, which is neither positive nor negative, but it is a whole number. So all exponents are 0 or greater. They're integers, which are whole numbers. And we see that these are the graphs down below. So the graphs of these polynomials have n behavior if the degree of the polynomial is odd. That means if the highest exponent in the polynomial is odd, it will be a degree that is odd and have opposite ends to its graphs. So we see that this is a first degree graph, this is a third degree graph. Notice they're on opposite ends. This is a fifth degree graph. So the end behavior is always on the opposite sides, where even degree graphs are always have ends that go to the same sides, both go up or both go down. Now, all of these examples are positive lead coefficients. If we were to change the lead coefficient to be negative, then it would flip the graphs around. And the same thing for the even degree graphs. If it had a lead coefficient that was negative, then the graphs would be pointing down instead of up. So we're going to use this table of data to do a polynomial regression. And we've done linear regression before in quadratic. Now we want to do degrees higher than 2. And we're going to use GeoGebra to help us with this. So GeoGebra allows us to type all of the data into a spreadsheet and then generate a polynomial. Here's the web address to the GeoGebra spreadsheet I'll be using. And once you have your spreadsheet open, you're going to type your data into columns A and B. Here's the data from the problems. You can pause the video here and type it into your spreadsheet. So now that I have all of the data typed into the spreadsheet, it says select the data and highlight it with your mouse. So I'll click on the first cell and hold down and drag until everything is highlighted. And next we want to click this toolbar. And then next to it here is what's called the two-variable regression. That's the one that we want, the two-variable regression analysis. And we see it opened up a window over here on the side. And we've got all of the points plotted. So it took the A column as the X value of the points and the B column as the Y value for the points. So underneath our regression plot or stat plot, it says regression model none. We're going to choose polynomial. And by default, it puts a second degree polynomial, which is quadratic. We've done quadratics. Notice how it's missing this first point. It doesn't fit the points quite as good as it could. And if we choose the next highest degree, see how it fits the points better. So degree 3 is what we're going to use, but just to explore a little bit, will degree 4 fit? And we see, yes, it does. Just notice the difference in the end behavior. Here it's curving like a quadratic, and here it's curving like a cubic, more of an S pattern. Now, I can keep going to higher degrees, and they all fit the data pretty much the same, but notice down on the bottom our polynomial equation has a 0 in front of the fifth degree. That means this coefficient, it's really not 0, it's just a very small decimal that the computer just shows as a 0. So that's kind of overboard. Fourth degree and third degree would be the choices I'd go with. But even if you look at fourth degree, the lead coefficient is 0.0002. It doesn't really give us much benefit over third degree. So why not make the function a little bit simpler to work with one less term? We'll choose the third degree polynomial. It fits all of the data very well. Again, just to recap, the quadratic was missing this point completely, a couple of points completely. So the cubic becomes a better fit. And that's something that's true of regression models. When you boost a degree higher, it will fit the data better and better, meaning that it'll actually intersect more points. So we'll stay with the third degree for this example. Now we can export this to our actual plot sheet. So this is the regression feature, but we're going to put it into the coordinate plane. I'm going to go full screen mode with this for a moment. And this is the button right here. It says copy to graphics view. That's what we want. We don't want to export as a picture. We want to copy it to the graphics view. So this is the export button, copy to graphics view. Now you see that it's shown up over here. Once we've copied it to graphics view, we can close the scatter plot feature. That's what these three buttons over here are for, and we can hit close. Now click any white space of the graph, and you can choose to move the graphics view. All right, I'm going to go back to my presentation, and I'm just going to drag this until it's in view. Good. So let's see. We exported to graphics view, then we closed that window. We took note of our polynomials earlier when we were comparing the different degrees. And now we can readjust, which we've done to make it viewable. And we can set a background grid. So this is the graphics button that lets us change the background. For this to work, you have to click on the background first, and then the graphics button, and we can choose. For us, we want the rectangular graphics background, and then I'll click this to close it. Okay, so there is the graph of our stat points and our polynomial function. If we want to see the actual function that draws this curve, we can, I'm going to go back to full screen mode. We can come up to this menu bar, go to the view menu here, and choose algebra. And I'm going to expand this algebra pane. So we see that g of x is the fit polynomial. So that's the polynomial that's made to fit here. It's 0.01x cubed minus 0.21x squared plus 3.23x minus 17.54. That's the cubic polynomial. We can view this through the algebra pane. And then this is the list plot, all of the points. Notice A1, B1 gives us the first point. A1, B1, that's 10, 5. And then A2, B2 gave us the second point. It's 14, 12, and so on and so forth. So the algebra pane shows us all of these lists that were used to plot into the graphics pane. So the next slide introduces us to rational functions. A rational function is any function that can be written in the form f of x equals n of x over d of x, where both n of x and d of x are polynomials. The domain is a set of real numbers such that the denominator d of x is not equal to 0. So they've given us some graphs to look at down below. Example A, we have f of x equals x minus 3 over x minus 2. That gives us this split graph. We call these branches of the rational functions graph. And these dashed lines are the asymptotes. And again, here we can see the vertical asymptotes. For example, b, the horizontal asymptote happens to be on the x-axis. And b is the function 8 over x squared minus 4. And c is a mixed function. But if we were to combine this to be a single fraction, we would get like denominators. So we would have to multiply x by x over x, and that would give us x squared over x plus 1 over x. And now that the denominators match, we can say that f of x equals x squared plus 1 over x. So when you have like denominators, you can combine the numerators. This is equivalent and the same as x plus 1 over x. And we can see the graph has what's called a slant asymptote, and it also has a vertical asymptote on the y-axis. So example 2 asks that we graph this rational function. The rational function f of x equals 3x over x squared minus 4. Part A says to find the domain. So what values will cause 0 in the denominator? So we set x squared minus 4 equal to 0. We can factor this. This is the difference of two squares. And we see that when x is equal to negative 2 or when x is equal to 2, we'll get a 0. So the domain is x not equal to plus or minus 2. And again, that means x can be all real numbers except 2 or negative 2. Next, it asks that we find the x and y intercepts. So when we plug in 0 for x, what do we get for y? And when we plug in 0 for y, what do we get for x? So we can see that when we plug in 0 for x, we get 0 over negative 4. 0 over negative 4 is 0. So that will be one of our intercepts. And when we plug in 0 for y, we're really replacing f of x with 0. So 0 equals (3x over x squared minus 4). And a fraction is 0 when the numerator is 0. So 0 equals 3x. So 3x is 0 only when x is 0. So the x and y intercepts are the same. They are at the origin. Now, part C says find the equation of all vertical asymptotes. The equations of the vertical asymptotes are the excluded values. That means these are the values that x cannot be. And if we recall, x equals negative 2 is a vertical line, and x equals 2 is a vertical line. So we'll put in our asymptotes. Part D says if there is a horizontal asymptote, find its equation. And we will go over how to find horizontal asymptotes. For now, I'll just explain it to you, and then we'll look at the actual theory behind it. We compare the degree of the numerator, which is degree equal to 1, to the degree of the denominator, which is degree equal to 2. If the degree of the numerator is greater than the denominator, we have a slant asymptote. If the denominator degree is greater than the numerator degree, then we have a horizontal asymptote through the x-axis, or y equals 0. And if they have the same degree, so let's for a moment suppose this was 3x squared over x squared minus 4, you take the lead coefficients, and 3 over 1, we take their ratio, and that would tell me there is an asymptote at y equals 3. So if numerator degree equals denominator degree, then the horizontal asymptote is y equals the ratio of the coefficients. And we'll see all of this laid out in notes again later. But for now, we see that our asymptote is at y equals 0. So we'll put an asymptote right through the x-axis. So part E says using the information from parts A through D and additional points as necessary, sketch the graph of function f. So we only have one point, and that's 0, 0. We need to choose points from the left side of the asymptotes, from the right side of the asymptotes, and from in between. So let's construct a table from the left side of the asymptotes. We'll choose -4. From the right side, we can choose +4. And from in between, I want to choose points both on the left and the right of 0, 0. So -1 and +1. So now we'll find the y values that go with each of these. So if you plug -4 into the function f of x, you'll get -12 over 12, which is -1. If you plug +4 into there, you'll get 12 over 12, which is +1. If you plug -1 in for x, you'll get -3 over -3, which is +1. And if you plug +1 in, you'll get 3 over -3, which is -1. So I'm going to plot each of these points: -4, -1, +4, +1, -1, +1, and +1, -1. So from this graph, we know that asymptotes are there to control and direct the branches of the curve. So the left and the right side are easy to graph. The reason we needed extra points in the middle is that in between the asymptotes, you can get S patterns, parabola patterns, any of these can exist in between. So we need additional points when we're in between asymptotes. And now that we have those points, we can go from the origin and say this will be an S pattern up to the left and down to the right. And that's the graph of our function f. And to verify this, we can plot it into our calculator to see how we did. So we'll hit y equals, and we'll type in parentheses 3x, close the parentheses, divide, parentheses, x squared minus 4, close the parentheses, and hit enter. You use parentheses to encase everything in the numerator and everything in the denominator, and that's to make sure that the order of operations are preserved. And then we hit graph. And if we compare this to our graph, we see we have the same branches in the lower left and upper right and the S pattern in between, so we've graphed it correctly. So here's the procedure for horizontal and vertical asymptotes. I described these saying that if the numerator degree and the denominator degree are the same, then we would use the ratio of a over b, where a is the coefficient of the numerator and b is the coefficient of the denominator for a horizontal asymptote. If the numerator is less than the denominator's degree, then y equals 0 is the horizontal asymptote. And if the numerator degree is greater than, there's no horizontal asymptote. It's actually a slant asymptote. And again, the vertical asymptotes are when you take the denominator, set it equal to 0, and solve, and you'll get your vertical asymptotes. So here we're just finding the asymptotes for this, vertical and horizontal. So we can start vertical are the easiest. Just take the denominator, set it equal to 0, and then we'll factor. And when we solve for each factor equal to 0, those are the locations of our vertical asymptotes. Remember, the domain would exclude these, but we would draw dashed lines for the vertical asymptotes. Now, the horizontal asymptote, find the largest exponent in the numerator and the largest exponent in the denominator. Since they match, take the coefficients and say that the horizontal asymptote is y equal to 3 over 2. So 3 over 2 is 1.5. So the horizontal asymptote would run through about 1.5, and the vertical asymptotes would run through -1 and 1. And then we would just need to find points on the left of the vertical asymptote, on the right of the vertical asymptotes, and then I would choose 3 points in between to see if it's a parabola or an S-shaped graph in between the asymptotes. So example 4 is an application of rational functions. It says a company that manufactures computers has established that on average a new employee can assemble n of t components per day after t days of on-the-job training as given by this rational function. Sketch the graph of n on the domain from 0 to 100. Include any vertical or horizontal asymptotes. And what does n of t approach as t increases without bound? When we say as t increases without bound, that means as it goes to infinity. We are using a domain of 0 to 100, so that's our x-axis. And the vertical asymptote comes from the denominator, so t plus 4 equal to 0 gives us t equals -4. Well, our x-axis is t, and they want us to stop at 0, so we will not see this vertical asymptote. Now we want to look for any horizontal asymptotes, and since the degree of the denominator is 1 and the degree of the numerator is 1, we take the lead coefficients, and we can say that the horizontal asymptote is y equals 50 over 1. So we'll go up to 50. And this is our n of t, which is the number of components at time t that a new employee can manufacture. So now we just want a couple of points between 0 and 100. So n of 0, if we plug in 0, we get 0 over 4, so that's 0. If we plug in 10, n of 10 would give us 500 over 14. 500 divided by 14 gives us 35.7. So we'll say about 36. So we have a point somewhere around there. Let's jump to 50 days in. And a 50 would give us 50 times 50 in the numerator and 50 plus 4 in the denominator, and gives us 46.3. So approximate 46. And let's look at n of 100. So I'm using parentheses to keep everything in the numerator. And then I divide and use parentheses to keep everything in the denominator. So 50 times 100 over 100 plus 4 gives us about 48. So it looks like our graph goes like this. And if we go off to infinity, what would you say is the maximum number of parts that an employee can manufacture in a given day as their time working for the company increases? And we should say that that answer is the horizontal asymptote, so a max of 50 parts per day. So this is the end of the lesson. As always, review the video with the guided notes, complete the practice, and write down questions to bring to the next class.